Swayam Prabha. Digital India. Educated India.
So welcome to today's lecture on basic control systems for mechanical engineers. Last class we studied about root locus. So today we are going to continue with that and then see how we can design controllers using the concept of root. Now let us consider an example where we will study the root locus. So let us consider the system L of S is equal to S plus 1 divided by S square into S plus 9. So let us draw the root locus. So first we will focus on the S plane. So first we will draw the pole 0 map for this system, which has 3 poles 1 0, and this corresponds to 3 branches. 2 of them go to infinity and 1 ends at a 0 of the system. So we will draw these poles. At 0 there will be 2 and you will have 1 at minus 9 and you will have a 0 at minus 1. So this is our pole 0 map, 2 zeros at S is equal to 0, 1 at minus 9 and a 0 at minus 1. So now we want to understand what part of the loci will be on the real axis. So if you see the positive real axis, you will see that there are no poles or zeros. So under those conditions, there will not be any part of the loci on the real axis. Whereas if you see between minus 1 and 0, there is an even number of poles and zeros on the right hand side. So that will not be a part of the loci. Between minus 1 and minus 9, there will be 3 poles and zeros. So it is an odd number. So that will be a part of the loci. So loci covers real axis minus 9 to minus 1. And beyond minus 9, since there is an even number of poles and zeros, that is not a part of the loci. Now since there are 2 branches which will go to infinity, we will have to find alpha, which will be minus 4, and the 2 asymptotes will make an angle of 90 degrees and 270 degrees. So let us draw minus 4 here. So say this is minus 4. So you have one asymptote going 90 degrees and the other 270 degrees. So now with this information, we will try to draw the loci. So the first one will start from 0, the pole on 0, come to some location here just before minus 4, and then we will go all the way to this 0. Then the other one coming from, then the next one will come from 0 and will be symmetric to this, but once it comes on the real axis, it will go to 270 degrees along the asymptote. And the last one will start from minus 9 come to this point of intersection, and then we will go along the asymptote which goes to 90 degrees. And in this way we have plotted the root locus for this particular example. Now let us consider another example where L of s is equal to s plus 1 divided by s square into s plus 4. And we will now plot the root locus. If you observe, the difference between this example and the previous one is that we have changed the location of one pole, that is, it's instead of minus 9 it is now at minus 4. So same thing, 3 poles, 1 0, so 2 poles at 0, 1 at minus 4 and a 0 at minus 1. We will have 3 branches, 2 going to infinity, 1 to the 0. And similar to the last case, loci covers in the real axis minus 4 to minus 1. In this case, alpha will be minus 3 by 2 and phi 1 will be 90 degrees and phi 2 will be 270 degrees. So we can plot, this is minus 3 by 2, one asymptote goes to 90 degrees, the other goes to 270 degrees. So now if we consider one root locus starting from 0, we will go along the positive asymptote. Similarly, another one starting from 0, we will go in a symmetric fashion to 270 degrees asymptote, and then here we will start from minus 4 and go to the 0 at minus 1, and so we have completed our root loci. Now as I had mentioned earlier, only the pole location has changed between these two, and what we observe, that if we observe this, we will see clearly that if we observe here, we will see that the root loci was also shifted from towards the right, because the pole has shifted towards the right. So what we can conclude, that pole approaching from far left tends to push loci branches to the right as it approaches the given locus. This is because so basically shifting the pole from minus 9 to minus 4, that is from the left towards the right, has shifted the branches of the root loci rightwards, and this is because of the expression for alpha, which depends on the pole location. So alpha has changed from minus 4 to minus 3 by 2, and we based on this we can come to this conclusion. In a similar manner, addition of zeros pulls locus into the left half plane. So, in the poles it takes it to the right half, now it is coming to the left half. So, let us consider one example for that. So, let us consider L of S is 1 by S square. So, in this case what happens is we basically have two poles at S is equal to 0, two poles, no zeros. So, both the branches go to infinity. For the part on the real axis is only S is equal to 0, because if we look at along the real positive real part, there are no poles or zeros, so that is not a part. If we look at the negative real part, what you will see is towards the right there is a even number of poles. So, that is the reason only S is equal to 0, that forms a part of this root loci. For this we have alpha is equal to 0 and phi 1 is equal to 90 degrees and 270 degrees. Phi 2 is equal to 270 degrees. So, for this case what happens is the first loci goes in along the positive imaginary axis, the second loci will go along the negative imaginary axis, and this way we get the root loci for this system. So, now let us consider a second example where we have the same pole locations, but now we will add a basically a 0 at S is equal to minus 1. So, based on this we will first start with the pole 0. So, we will have two poles at the origin and there will be, sorry for this, and there will be a 0 at minus 1. So, basically there are two poles, 1 0, one branch ends at S is equal to minus 1, other goes to infinity. The part between, if we look at for the real axis, the positive real axis is not in the loci. Between minus 1 and 0 there is an even number of poles, whereas if we look from minus 1 to infinity, rather negative infinity, that part is basically will lie on the loci, because the sum of poles and zeros is equal to 3, that is an odd number. So, once we have this part, we can plot the root loci. So, one of the root loci goes along this direction and will come to this 0. The other one will in a symmetric fashion will get something like this, and this will go to infinity. In this case alpha will be equal to half and phi is 180 degrees. So, 180 degrees means it is along the negative real axis. So, now we can see what this has done is, when there was no 0, we had everything along this imaginary axis, the entire root loci. Now with the addition of 1 0, it has moved sideways, it has moved into the left half plane, and this can be also seen from basically the formula. These two observations we have made based on these examples, this is the first one and this is the second one, can also be seen using this particular formula for alpha, which was for the asymptotes, that so this formula tells us is that as the poles start from the left hand side and move towards the right hand side, this part will go on decreasing with respect to alpha, and alpha will tend to move towards the right hand side. Similarly, as we add the values of 0, will get subtracted and they will move towards the left hand side. So this formula justifies these two observations which we have made from this example. And now we are going to use this particular two observations and what we have concluded here, which will help us in design of controllers. So far we have seen root locus. Now let us see how we can design controllers using that. So first let us we'll start with an example. So we have L of S is equal to 1 divided by S plus 1 into S minus 3. So if we plot the root locus for this, you will see here that there are two poles. One is at S is equal to minus 1 and the other at S is equal to 3. No zeros. So there will be two branches. Starting at poles and going to S tends to infinity. And the real part will be if you go beyond 3 on the positive real axis, that is this side, there is no poles or zeros, so that part is not a part of the root loci. Whereas if you are between minus 1 and 3, you will have an odd number of poles. So this part from minus 1 to 3 will be covered here. And if you go beyond minus 1 this side, what you will see is there is an even number of poles on the right hand side. So you are not going to cover that part. So the only part which is covered as part of the root loci is this from minus 1 to 3. Now there will be asymptotes, right, because n minus m is equal to 2. So in that case you will have alpha, and in this case it is equal to 1. Then we have phi 1 is equal to 90 degrees, phi 2 is equal to 270 degrees. So what you will see in this case, we will start with the first one from 3 and let us assume that it goes 90 degrees. The other one starts from here, goes 270 degrees. So here you will see in this example that this particular system is unstable for all k. As for each value of k, the location of the closed loop poles lies in the right half plane. And basically, if we are just given this system and we consider that a controller is only a constant gain, then the poles of the closed loop system have to just move along this root loci. But we can change the path of the root loci by considering an alternate structure for our controller. So, how we can go about that is, let us say we have seen in the previous, so we do not want the root loci, the entire part of the root loci to lie in the RHP, right. So, we want to move it towards the LHP. Now, if we look at the previous scenario here, what we have seen that by adding a 0, we can pull the loci into the LHP. So, let us consider adding a 0. So, what we do is we consider, so our earlier system was S minus S plus 1 into S minus 3, right. Now, to this what we do is we add a 0, say at S is equal to minus 3. So, in this case the root loci is something of this form. We will have two poles. So, here we have 3, then minus 1, minus 3, 2 poles, 1 0. One path starts from pole, ends at 0, other path starts from the other pole and goes to infinity. Now, coming to the real part, we can see that beyond this part there is nothing on the root loci. Between minus 1 and 3 we will have part of the root loci. Between minus 3 and minus 1 there are an even number of poles. So, that is not part of the root loci, and going beyond minus 3 what you will see is there are even number of poles and zeros. So, that will be also a part. So, going from say the negative infinity to minus 3. So, this is also a part of this root loci. Now, coming to the value of alpha. So, in this case it will be really 3 minus 1 plus 3 is equal to 5, and phi 1 will be equal to 180 degrees. So, basically the asymptote is along the negative real axis. So, in this case what happens now is one of the loci will start from here, the other one in symmetric fashion go from here to here. Then this part of the loci will similarly in a symmetric fashion will come here, and this angle here will be 90 degrees. One part of the loci, so we are assuming that this one goes here and the other one will go to infinity. So, basically what we have done between these two examples is, here the entire part of the root loci was in the RHP, so resulting is unstable system for all values of k. Now here what happens, for small values of k, what you will see is there is, it will be unstable, but as the value of k increases, that is it crosses these 2 points, the system will the closed loop system will be stable and will get a stable closed loop control system. So that is possible with understanding of these two rules and the root loci. Now this kind of a controller will be something of the form k into s plus 3, which if you see from what we have studied in previous class, represents a PD controller. So here this k into 3 represents a proportional gain, and this just k represents the derivative gain. But a derivative gain by itself, the proportional derivative, is sometimes not ideal, because the derivative can amplify the noise resulting from the sensor. So in that scenario, what we do typically is we use a controller of the form, we divide this by s plus p, where p is the pole of the controller parameter, which we need to decide based on the specifications. So these kind of a controller are called lead lag compensators, and their general structure is of the form, there is some gain times s plus z divided by s plus p. This is a lead compensation if z is less than p, and it is a lag compensation if z is greater than p. So these lead compensation is basically used to compensate for the transient response, that is get a desired transient response, whereas the lag compensation is more concerned with the steady state. So we will see how to design these lead lag compensators based on what we have discussed about time domain specifications and the root loci using an example. So let us consider the scenario where we take that our maximum overshoot should be less than or equal to 20%, and similarly the rise time should be less than or equal to 0.3 second. We know MP is equal to e to the power minus pi zeta 1 minus zeta square. We have seen this in the prior lectures. Similarly, TR can be approximated as 1.8 by omega n. And if we do these calculations, we find that zeta is greater than or equal to 0.5 seconds and omega n is greater than or equal to 7 radians per second. Considering these as our design objectives for this particular system, let us design a controller. So let us first start with d of s is equal to k. So in this case, we can come ahead and plot its root locus. So this is the real axis, imaginary axis. In this case, there are two poles, one at s is equal to 0, other at s is equal to -1. So, sorry, there are two poles, one is at s equal to 0, second is s equal to -1. There is no 0, two branches going to infinity. The real axis part in this case, it will be the positive real axis has no poles or zeros, so that's not a part of the loci. From -1 to 0, you will find that at the right side there is only one pole, and beyond -1 there is an even number of poles, so we are not going to consider that as a part of the loci. So only this part is a part of the loci. Now there will be two asymptotes, so we need to find the value of alpha, which will be -half, and phi 1 will be 90 degrees, phi 2 will be 270 degrees. So we can plot the root loci. So it looks something of this form, a rough sketch of the root loci we have got. Now if we see these particular specifications, what you will find is this zeta greater than 0.5 implies that we are going to have a line at 30 degrees here. So as we have discussed in the previous lectures, it will lie in this side. Similarly, omega n greater than equal to 7 radians implies that basically we are going to have at a radius, sorry, need something. So it will be beyond this semicircle. So if you go on projecting these lines ahead, right, what you will see is when it crosses this semicircle, the angle here, it's much smaller than these 30 degrees of what we intend. So just assuming d of s is equal to k, there is a constant gain, will not meet our specifications. So proportional gain does not satisfy specifications. So in that scenario, we do what we have done in the last example. So what we try to do, we want to move our root loci to the left side, right? So as discussed, we add a 0 to get a PD controller. So let us say that now our L of s, or rather we assume our D of s to be, instead of k, to be s k into s plus 2. So in that case, our L of s will be s plus 2 divided by s into s plus 1. So in this scenario, we can plot the root loci, the real axis, imaginary axis. We have two poles, s equal to 0, s is equal to -1, and we have 1 0 here at s equal to -2. So what in this case what happens is, so basically there are two poles 1 0 and n minus m is equal to 1. So basically there will be one asymptote. So one branch goes to infinity, other goes to 0. This is scenario, we start from here. So the angle will be equal to 180 degrees. In this case alpha will be equal to 1, and the real part will be from -1 to 0, because there is on the right side there is an odd number of poles and zeros, whereas from -2 to -1 that's not a part because there are even number of poles, and from negative infinity to -2 it's part of the root loci because there is an even number of poles and zeros. So the first branch of the root loci starts from here, the second branch will start from here and go in this direction, and after that this branch will come here and say go along this direction. Similarly, symmetric fashion, this one comes here and goes along. So now in this scenario, if we make the necessary look at the necessary specifications, it's possible to meet these specifications. But as we had discussed earlier, k into s plus 2 is basically a PD controller and not desirable. So in this scenario what we do is we use a lead compensator. So we have s plus p. So this is the lead compensator. Now what we need to do is find this location of p such that we can try to meet our specifications. So what we have discussed is we can with the addition of 0 move the root locus to the left hand side and possibly be able to meet these particular time domain specifications. But we also need a pole, because just with the addition of 0 this becomes a PD controller which is not advisable. So we formulate a lead compensator. So now to doing about that, we consider different scenarios. So first we consider this p can take various values, right? So we can consider scenarios like the value of p is equal to 10, 13 and maybe 20. So first let us start with the value of p is equal to 10. So in that case L of s is equal to s plus 2 divided by s into s plus 1 into s plus 10. So now if we look at the root locus, there are 3 poles and 1 0. So here we have one pole at 0, the other one is at -1, and we have a far away at equal to -10, and we have a 0 here at -2. So two branches go to infinity. The real part along the real axis, the positive, there is no pole or 0, so we are not going to, that won't form a part of this root loci. -1 to 0 forms a part because there is only one pole on the right side. -2 to 1, there are even number of poles, so that's not a part. From -10 to -2, what you will find is there is an odd number of poles and zeros. So that's a part of the root loci. So here and here. So the first part of the so another part is the value of alpha, which in this case will be -9/2, and phi 1 will be 90 degrees and phi 2 will be 270 degrees. So we plot, we have to see the asymptote at -9/2. So this is -9/2. So now this first here starts, one of the root loci will start from -10 and go all the way up to -2. The next one will start from 0 and then go along it will start from 0, come here and then go asymptotically. The next one starts from -1, goes here and then symmetrically will go along. So now if we make those specifications of having our specifications that omega n should be greater than or equal to 7 radians, what we can do is something of this one. So it will intersect our root loci and the angle will be greater than 30 degrees. So both specifications are met. So basically for a gain equal to 70, we get zeta is equal to 0.56 and omega n is equal to 7.7 radians per second. So this is basically acceptable to us. So based on this time domain specifications which we have been given. Now if we plot the step response for this particular system, we get some step response of this form. So this is r of t and this is y of t, what we have seen in the previous lectures. But what you will find is this particular part is greater than 20%. So this is basically greater than 20% here. And our specification was that it should be less than 20%. So why is that? That is because these specifications, these formulae basically when they were derived for pure second order systems with no zeros. But here if you check this particular system, there is a 0. So that acts, so that is the reason we do not get this value to be less than 20%. So we need to do we need to consider some other cases. So let us say in this scenario we consider L of S to be S plus 2 . So as I mentioned earlier, P can take many values, say 10, 13, 20, 25 and so on. So let us consider the case where P is equal to 13. So for this case we plot the root loci. So we basically now have 3 poles and 3 branches to go to infinity. So basically we will start here 1, another one here, all the way up to here, say this is minus 13, minus 1, 0, and we have a 0 here at minus 2. So if we consider the real part, the positive side, as we have seen, there is no pole 0, so that's not a part of the loci. From minus 1 to 0, that's a part of the loci. Similarly, if we consider from minus 13 to minus 2, that's a part of the loci. In this case, alpha is equal to minus 6 and phi 1 is equal to 90 degrees and phi 2 is equal to 270 degrees. So we can get this at minus 6. So the first branch starts from here, goes all the way up to here. The second branch will start from here and this is the first branch. The second one will start from here and go all the way up to here. The third one will start from here in a symmetric fashion, go here. So these are along minus 6. So now in this scenario, if we select k is equal to 91, what it gives us is MP is equal to 17%. So this is less than 20%, right, basically. So this meets our specification. So this choosing the pole or the 0 location in this compensator can at times be a trial and error method. So you will have to plot the root locus as well as the step response and see how it performs. So you can start with an initial guess based on the root loci, accordingly plot once you get the gains and the pole 0 location, you can plot the step response. If it does not meet the specifications, you will need to iterate a bit based on the knowledge of your knowledge of root loci. And once you get another result, you perform the same step, plot the step response, and this continues till you get a satisfactory result. So now we have found this controller which meets our time domain specifications. Now say in addition to these time domain specifications, I have what is a steady state error specification. So first let us calculate what will be the steady state error in this case. So, that will be limit s tends to 0 s k d g, as we have discussed in our in the previous lectures. So, we get limit s tends to 0 s k in this case is 91 s plus 2 s plus 13 and g is 1 divided by s into s plus 1. So, if we plug in the values, we find that this value will be equal to 14. Now, suppose we want, based on our steady state error specifications, that this kV should be 70. So, the desired value of kV is 70. So, how do we go about that? Do we change the entire lead compensation or change the pole 0 locations? So, in this case, what we do is we have this lead compensator, to that we augment a lag compensator, because the lag compensator takes care of the steady state. So, what we do, we want Kp should be basically 70. So, we can use a lag compensator such that if we look at the structure of the lag compensator, it is some k is s plus z by s plus p, where z is greater than p, and we want to go from 14 to 70, and this is, as you can see, s tends to 0. So, if we put s is equal to 0 in this expression, ideally what we want is for z by p to be equal to 5. Now, you could say, okay, z by p is equal to 5, but what is the multiplying factor? For example, you can place the 0 at 5, pole at 1, you can place the 0 at say 50 and pole is at 10. So, we want to do this z by p is equal to 5 in such a way that we do not affect this existing root locus. So, for that what we will do in this case is select z is equal to minus 0. Basically z is equal to, sorry, should be plus 0.05 and pole to be 0.01. So, we have additional compensator s is equal 0.05 divided by s 0.01. So, our overall compensator will be 91 into s plus 2 by s plus 13 s plus 0.05 divided by s plus 0.01. So, now if we plot the root locus, for a greater part it will be very similar to what we have here. The only thing is we will have these 0 and pole at 0.05 and 0.01. So, with that we will conclude today's lecture. Thank you.
Hello and welcome to this piece of literary snippet. Perhaps the most popular literary genre after novel is the short story. Sharp, compact narratives whose charm lies not only in what is said but also in what remains unsaid. Today I'll be reading one of the shortest instances of a short story that I have ever encountered, and indeed the very charm of this particular story that I am going to read out today lies in the way it abruptly ends. It is an ancient tale from Mesopotamia which has been retold by several authors, among whom the name of Somerset Maugham stands out. The adaptation that I'll be reading out is perhaps the closest to the one that Maugham wrote. The story is titled, in all of its adaptations almost, as Appointment in Samara. Here is the story. A merchant in Baghdad once sent one of his servants to the market. The servant was supposed to buy provisions for the merchant, but when he returned, he came back empty-handed. Indeed, the servant had all gone white, and trembling with fear, he told his master that he had met death in the marketplace. When I entered the market, the servant said to his master, I was jostled by a woman, and when I turned to look at her, I saw that she was death. I am very scared, master, because death looked at me with a threatening gesture. Can you please lend me your horse so that I can fly away from Baghdad to the town of Samara and thereby escape death? The master, being a good man, gave his servant his best horse and saw him gallop off to Samara to escape death. Then the master himself went to the marketplace and confronted death. Why did you make a threatening gesture to my servant? Asked the master to death. And death replied, it was not a threatening gesture. Rather, it was a start of surprise. I was astonished to see your servant here today, because this evening I have an appointment with him in Samara. See you in the next episode of Literary Snippet.